Okay, let's take a look at the divergence and curl. And I don't even need to say in R3 because the divergence and curl are generally understood to be in R3. But here, to make it explicit, we're looking at it in R3. And our vector field now is defined in R3. So we get three components. The divergence formally is written out this way. You could take this, it's called the del operator. Okay. And it's this partial x, partial y, partial z. And again, this thing is not a real vector, okay? But you could use it symbolically and formally to get this expression, okay? If you take that dot product. The curl is defined this way, okay? You have now I, j, and k there, and you're taking the curl between this del operator and the vector field f, and you end up with this expression, okay? And I make an important remark here. The curl is a vector field, okay? Curl is a vector field, okay? Whereas the divergence is a scalar function, or sometimes called the scalar field. Okay, so this is scalar, whereas the curl is a vector field. Let's take a look at an example of taking the divergence and curl of, say, this vector here. Okay, and if we take the divergence, you would just use this formula that we have here, with f being the x component of the vector field, and on and on. So we have minus y for that, partial y, partial x, and partial z. And you get, for the divergence, the scalar function. Okay, this actually depends on x, y, and z, but trivially, because they're not in the expression, it's equal to 1. Okay, we could also take the curl of this vector field, and again, you set it up now. Here's our vector field, so you go through with these steps, and you end up with this vector field 0, 0, 2, and this again could arbitrarily depend on x, y, and z. I write, although the curl and divergence are constant, here they're the constant vector field. Okay, these are constant this is a constant vector field, and this is just a constant scalar function. In general, they don't have to be that. Okay, so you could have had some complicated expression of x, y, and z in for this. Okay, and in brackets here, because it's a vector field, a complicated expression of x and y and z in each of the components. Also, to note here, a vector field is called irrotational or curl-free when its curl is 0. And the vector field is called source-free or divergence-free or solenoidal, okay, when its divergence is 0. And we will be using these facts for important reasons here. So let's take a look at this vector field here. That's the spiral flow one. That's the one that we just computed the divergence and curl of. Okay, and for the divergence, we got that the divergence was equal to 1. And if you'll recall, that was coming from this last term, that the z component depended just on z of this vector field. So we had partial z of z is 1, and that's how we got a divergence equal to 1. It was the z component that was responsible for that. And when you take a look at the vector field, you could sort of see why. As you'll recall, the divergence is a measure of expansion and contraction, okay? Sources and sinks. So along the z-axis, the vectors are pointing farther along the z-axis, so they're pointing up more as you move in the positive direction on the z-axis, and pointing down more as you move along the negative z direction. Okay, so you're sort of getting this expansive effect, and that's what gave us the divergence of 1 there. Now, the x and y component they didn't really contribute to the divergence. And if we rotate this vector field, and look at it from above, you can see why. The x and y components are just rotating around. They're not responsible for any expansion outward or contraction inward. They're just rotating around. And so they didn't really contribute to the divergence. They did contribute to the curl, okay? And if you'll recall, the curl, we computed, it was the constant vector 0, 0, 2. Okay, we had a 2 in the z component. And how do you get the z component? Well, the z component is partial x of the y component minus partial y of the x component, okay? And so that gave us the 2, okay? They contributed to the curl, okay? And it points in the z direction because in rotation, if some of you maybe want to build on the physics intuition, if something is rotating, its rotation vector, angular momentum, points perpendicular to the rotation. And that's what's going on over here. And these rotations are growing ever larger as you move farther away from the z-axis. And so we ended up having a curl there, the measure of twistiness of the field. And thanks to xy, we got the xy components, we got some twistiness along the z-axis, okay? And thanks to z, we got some sort of expansive behavior along the z, okay? The vectors were getting larger along the z-axis, and that contributed to the expansive effect. So divergence is a measure of expansiveness or expansion and contraction, sources and sinks, whereas curl is a measure of the twistiness of a field, the rotation. That's where your intuition should take you with regards to curl and divergence.